Let's talk about virtual particles. The name itself sounds a bit strange, virtual. Like they aren't quite real, and when you hear what they supposedly do, it gets even stranger. They pop into existence from absolutely nothing. They exist for a tiny fraction of a second. Then they vanish. This seems like a huge problem. One of the most basic rules we learn about the universe is that you can't get something from nothing. The law of conservation of energy. Energy can't be created. It can't be destroyed. It can only change form. So how can a particle, which has energy and mass, just appear out of the void? It sounds like it's cheating. It sounds like it's breaking the most fundamental law of physics. And the short answer is no, they don't violate the laws of physics. But the long answer is much more interesting. It tells us that the laws of physics are not what we think they are. Our common sense understanding of rules like conservation of energy is a bit too simple. The universe, at its smallest and most fundamental level, operates by a different set of rules. Virtual particles don't break the rules. They are a perfect example of what those deeper rules actually are. To understand this, we have to start with the rule they seem to break. Conservation of energy is a pillar of science. If you take a closed system, a box sealed off from the rest of the universe, the total amount of energy inside that box will never change. It can move around. Heat energy can turn into light energy. Potential energy can turn into kinetic energy. But the total number, the final sum, always stays the same. And thanks to Einstein, we know that mass is just a very compact form of energy. His famous equation, EMXE2, tells us exactly how much energy is locked up in a piece of matter. The kid in that equation is the speed of light, which is a massive number, and it's squared. This means a tiny amount of mass is equivalent to a huge amount of energy. This is why nuclear reactions are so powerful. They convert a tiny bit of mass directly into energy. The reverse is also true. If you have enough energy concentrated in one place, you can create matter. You can create particles. This happens in particle accelerators all the time. Scientists smash particles together at incredible speeds. The kinetic energy from that collision gets converted into the mass of new exotic particles. But there's a catch. You need enough energy to do it. To create an electron, you need at least 511,000 electron volts of energy. That's the price. No less. You can't create an electron with half that energy. The universe has a strict budget. You must pay the full energy cost up front. This is what makes virtual particles so baffling. They seem to ignore the budget. A virtual particle-antiparticle pair, like an electron and its antimatter twin, a positron, can supposedly just appear in empty space. The energy cost to create these two is over 1,000,000 electron volts. But they appear in a vacuum, where the energy is supposed to be zero. They are taking out a huge energy loan from the universe with no apparent way to pay it back. Then they disappear, and the loan is seemingly forgiven. This looks like a blatant violation of energy conservation. It's like a bank account that can go into a massive overdraft for a moment and then magically reset to zero with no consequences. For a long time, this was a deep puzzle. It seemed like either our understanding of energy was wrong, or this idea of virtual particles was just a fantasy. The resolution came from the weird world of quantum mechanics. Classical physics, the physics of billiard balls and planets, gives us clear, definite answers. If you know where a ball is and how fast it's moving, you can predict its entire future path with perfect accuracy. The rules are rigid. Energy is always conserved at every single moment, with no exceptions. But quantum mechanics threw all of that out. It describes the world of the very small, the world of atoms and electrons. And in that world, things are not so clear. Certainty is replaced by probability. A particle doesn't have a definite position until you measure it. It's more like a wave of possibilities. And one of the most important new rules to come out of this revolution was Heisenberg's uncertainty principle. This principle is the key to the whole virtual particle mystery. Most people have heard of one version of it. It says you cannot simultaneously know the exact position and the exact momentum of a particle. The more precisely you measure its position, the less you know about its momentum, and vice versa. It's not about having bad measuring instruments. It's a fundamental property of the universe itself. There is a built-in fuzziness to reality, but there's another version of the uncertainty principle. This one relates energy and time. It says that you cannot know the exact energy of a system for a very short period of time. Just like with position and momentum, there's a trade-off. The shorter the time interval you are looking at, the more uncertain the energy of the system becomes. Let that sink in. It's a profound idea. Our old idea was that energy is a fixed, precise number at all times. The uncertainty principle says that's not true. For very, very brief moments, the energy of a system can be fuzzy. It can fluctuate. The universe doesn't seem to enforce its energy budget strictly over tiny slivers of time. This is the loophole. This is how virtual particles get away with it. They are allowed to borrow energy from the vacuum, violating the classical law of energy conservation. But they must do it very quickly. The amount of energy they can borrow is inversely related to how long they can exist. If they borrow a lot of energy, enough to create a heavy particle, they can only exist for an unimaginably short time before they have to pay it back by disappearing. If they borrow only a tiny bit of energy, they can stick around for a little longer. The formula is roughly dE times dTAh for P. Here, dE is the change in energy, the amount borrowed. And dt is the time it's borrowed for, the Hitchens-Planck's constant, a very, very small number that governs the quantum world. This equation is like the universe's loan agreement. It says the product of the borrowed energy and the loan duration must be at least a certain tiny fundamental amount. So, a big loan large dE means a very short repayment times small dt. So, do they violate conservation of energy? In a way, yes, but only for a moment, and only within the limits allowed by the uncertainty principle. The principle isn't just an excuse, it's a more fundamental law than the old classical version of energy conservation. It's like finding out that the law isn't don't steal, but rather, if you steal, you must return it before anyone can possibly notice. Since the time is so short, no real-world measurement could ever catch the particle in the act of existing. The energy of the system before the fluctuation and after the fluctuation is exactly the same, zero. Overall, on any timescale, we can actually measure. Energy is conserved perfectly. The violation is temporary, self-correcting, and hidden within the quantum fuzziness of reality. This leads to the next big question. What even are these things? Are they real particles? The name virtual particle is a bit of a marketing problem. It's misleading. When we think of a particle, we think of a little dot, a tiny billiard ball. We think of an electron, a proton, a photon. These are what physicists call real particles. A real particle can travel through space indefinitely. It can hit a detector. We can measure its properties. It exists on its own. A virtual particle is not like that. It cannot be directly detected. No, it never hits a screen. You can't isolate one and study it. This has led many physicists to say that virtual particles are not real at all. They are just a mathematical trick, a useful fiction that helps us do our calculations. This view is very common and has a lot of truth to it. In the framework of quantum field theory, the most successful physical theory ever developed, particles are not the fundamental thing. Fields are. There is an electron field that fills all of space. There is a photon field. There is a Higgs field, and so on for every fundamental particle. What we call a real particle, like an electron, is a stable, persistent vibration or excitation in the electron field. Think of the field like the surface of a pond. A real particle is like a ripple that travels across the pond, maintaining its identity. In this picture, a virtual particle is a different kind of disturbance. It's a temporary, localized fluctuation in the field. It's a ripple that rises up and then immediately falls back, without ever breaking away and traveling across the pond. It's a disturbance that doesn't have enough energy to become a full-blown independent particle. It exists only as a momentary bridge between other events. The way physicists calculate interactions between particles is by using tools called Feynman diagrams. These diagrams are like little cartoons of particle interactions. You might have a line for an electron coming in, another line for another electron coming in, and they exchange something in the middle that makes them repel each other. That something they exchange is drawn as another line, and that's the virtual particle. In the case of two electrons repelling each other, they exchange a virtual photon. Every line and every junction in a Feynman diagram corresponds to a mathematical term in a very complex equation. The virtual particle is what's called an internal line in the diagram. It starts and ends within the interaction. It never flies off to be detected, and the math associated with that internal line describes a particle that doesn't obey the normal rules. It can have the wrong mass. It's what physicists call off-shell. A real electron always has a mass of 511,000 electron volts. A virtual electron in a calculation can have any mass, as long as it exists for a short enough time. So, from this perspective, a virtual particle is just a term in an equation. It's a part of a calculation method called perturbation theory. This method breaks down a complex interaction into a series of simpler possible events. The virtual particles are the intermediate steps in that series. They are a powerful and indispensable tool for getting the right answers. Without them, we couldn't calculate things to the incredible precision that we can. But does that mean they aren't real? If something is a mathematical tool, but it perfectly predicts real, measurable effects, what does that make it? This is where physics touches philosophy, and the evidence for the effects of virtual particles is overwhelming. We may not be able to see them directly, but we see the consequences of their existence everywhere. The most famous example is the Casimir effect. Imagine you take two perfectly flat, uncharged metal plates. You bring them very, very close together in a perfect vacuum. What should happen? According to classical physics, nothing. There is no force between them, but quantum field theory predicts something different. It says that the vacuum is not empty. It's a bubbling, seething soup of virtual particles constantly popping in and out of existence. Now think about the space between the two plates. It acts like a resonant cavity. Only virtual particles of certain wavelengths can fit between the plates. Longer wavelengths are excluded. But outside the plates, in the vast expanse of the vacuum, virtual particles of all wavelengths can exist. This means there are more virtual particles, more quantum fluctuations pushing on the outside of the plates than on the inside. This imbalance creates a tiny, but measurable net force that pushes the plates together. This is not a theoretical fantasy. The Casimir effect has been measured in labs with high precision. The results match the predictions of quantum field theory perfectly. The force is real. It's caused by the sea of virtual particles that fills all of space. So if their effects are real and measurable, how can we say they aren't real in some sense? Another piece of evidence is the Lamb shift. According to simpler quantum theory, two specific energy levels in a hydrogen atom should have exactly the same energy. But in the 1940s, Willis Lamb discovered a tiny difference between them. The reason for this difference, it turns out, is the vacuum. The electron orbiting the proton in the hydrogen atom is not doing so in a quiet, empty space. It is constantly interacting with the cloud of virtual particles popping in and out of existence around it. This constant jostling by virtual photons slightly shifts the electron's energy levels. The calculation of this shift, which involves virtual particles, matches the experimental measurement to an incredible degree of accuracy. Then there's the anomalous magnetic moment of the electron. An electron acts like a tiny spinning magnet. A simple theory predicts the strength of this magnet to be a certain number, but when we measure it, the number is slightly different. It's off by about 0.1%. Why? The reason is that the bar electron is surrounded by a cloud of virtual particles. It constantly emits and reabsorbs virtual photons. Sometimes, these virtual photons can momentarily split into virtual electron-positron pairs before recombining. All of this activity creates a complex virtual cloud that slightly alters the electron's magnetic properties. The calculations for this effect are among the most complex in all of physics. They involve considering all the possible ways the electron can interact with this virtual soup. And the result is the most precisely verified prediction in the history of science. The theoretical calculation and the experimental measurement agree to more than 10 decimal places. It's like measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. This staggering agreement gives us enormous confidence that the picture of a particle interacting with a sea of virtual fluctuations is fundamentally correct. So, where does this leave us? Do virtual particles violate the laws of physics? No. They force us to adopt a more sophisticated and accurate version of those laws. The simple, classical idea of energy conservation is an approximation that works well in our big, slow world. But the true fundamental law is the uncertainty principle, which allows for these fleeting energy fluctuations. Are they real particles? No, not in the sense that an electron or a photon is a real particle. They are not little balls that pop in and out of existence. That's a convenient but inaccurate story we tell. A better way to think of them is as the tangible effects of the underlying quantum fields. The vacuum is not empty. It has a structure, it has a ground state energy, and it is constantly fluctuating. These fluctuations, these temporary field disturbances, are what we label virtual particles. The name is the source of all the confusion. If they had been called transient field computations or quantum vacuum fluctuations, there would be much less debate. But virtual particle sounds so much more concrete, and it leads our classical brains to imagine things that aren't really happening. The best way to think about it might be this. The math of quantum field theory is the most accurate description we have of reality. That math is full of terms that we have given the name virtual particles, and that math makes predictions about the real world that are verified to an astonishing degree of precision. Therefore, whatever those mathematical terms are representing must be a real aspect of the universe. The Casimir effect, the Lamb shift, and the magnetic moment of the electron are not caused by mathematical fictions. They are caused by the very real, very dynamic nature of the quantum vacuum. Virtual particles are a language for describing that dynamic nature. They are the grammar of particle interactions, so they are not a violation of physics. They are a window into the deep, strange, and beautiful reality that quantum physics describes. They show us that empty space isn't empty. They show us that the fundamental laws of nature are written in the language of probability and uncertainty, not rigid certainty. And they show us that our simple, intuitive ideas about the world often break down when we look at the true fabric of existence. The rules aren't being broken, we are just finally learning what the real rules are. And they are far weirder and more wonderful than we ever imagined. The universe isn't cheating, it's just playing a different game.